Hi there, my name is Matthew Hall and I'm here today to present the work that I, along with my colleagues Anil, Ozdemir and Roderich, have performed on self-reconfiguration in 2 dimensions via active subtraction with modular robots. A nice long title with lots of concepts. I'll first introduce the modular robots part. It's a concept that I'm sure many of you are familiar with, if not from research, then maybe from Disney's Big Hero 6. But the idea is that relatively simple individual robots can combine together to create one larger robot that is more capable than the sum of their parts. And while we were way off being able to dangle children from the ceiling, it does give a good example as to why research into the field is so exciting and worthwhile. The modules you see here are reconfiguring through additive reconfiguration, where the modules come together and create connections to change the shape. But this has proved to be a complex problem without a reliable solution. So one way to come up with a more reliable and potentially simpler method of reconfiguration is through subtractive reconfiguration. Subtractive reconfiguration is more akin to a sculptor starting with a block of marble and chiselling away to reveal the beautiful sculpture underneath. In this case, it's robots being removed to leave behind the desired configuration. Research has already been done into this with modular robots, but in that case it was passive modular robots, so once the connections were removed, the modules had to be picked up by hand or removed by external locomotion. What we suggest here is active subtraction, where the modules disconnect and then remove themselves from the configuration. The structures that we are concerned with in this work use models of simplified modular robots. These modules are initially arranged in vertical, 2-dimensional rectangular structures. The types of modules in each configuration are included if they are to remain in the desired structure at the end, or excluded if they need to be removed. We present 2 solutions here, sequential active subtraction or SAS, where modules remove themselves in sequence one at a time, and parallel active subtraction, where modules are able to move simultaneously, but we still avoid any collisions or collapsing of the structure. The first solution I'll talk about is SAS, sequential active subtraction. In this solution, a single leader module is required in the configuration and is responsible for selecting which of the excluded modules is going to be removed. We also present an algorithm for the movement of this active excluded module. It requires only the local knowledge of the module's more neighbourhood, so it doesn't know where the sink is in relation to its position. It just checks valid movements on each side before moving it into the first location that it finds that it is able to. The second solution we present is parallel active subtraction, which builds on the concept in sequential active subtraction, still using a leader module which actually simulates SAS in order to obtain the order in which the modules are to be removed and the time it takes each module to reach the sink location. These values are used to perform simulations of the modules moving in parallel, and the leader module then accounts for any collisions that may occur in these simulations and delays the start times of each module accordingly. We prove both of these solutions mathematically in the paper, but that doesn't make for a very good video, so if you'd like to know more about the intricacies, please do feel free to read it. We also proved the performance with simulations. We ran simulations on predefined structures, which were similar to ones from other pieces of literature, as well as some interesting ones that we quite liked. Here you can see modules reconfiguring to a U-shape, with the sequential reconfiguration on the left and parallel on the right. Here you can see the reconfiguration of an inverted humanoid shape. You can see that on the parallel side, no collisions occur, and some of the modules that arrive later actually start movement earlier because they have so much further to travel. Finally, here's a 20 by 20 humanoid shape with the right foot lifted slightly. This sequential video here has been sped up by 10 times because it took so much longer than the parallel movement. From these simulations, it was determined that parallel movement obviously allows a much quicker reconfiguration, despite requiring more computational power of the leader module at least. We also ran simulations on randomly generated configurations, such as this one here, where we did sizes ranging from 5 by 5 all the way up to 25 by 25, and various inclusion densities, that is, the percentage of overall modules which were included in the final shape. The simulation results from those are also shown in the paper. So I've presented 2 solutions today to the problem of self-reconfiguration with modular robots using the novel concept of active subtraction, where modules will remove themselves to leave behind the structure. We hope to expand it into 3 dimensions and real systems before too long, but this is a great stepping stone towards that future work. Thank you very much for listening.